just hoping I copied the right thing. I think I did. All right, so to come up with my U matrix, it needs to be an echelon form. Right, so n echelon form. So these guys, we go column by column. These guys got to go. All right, so I need a negative 2r1 plus r2, a negative 3r1 plus r3, and a, well, 1r1, so just r1 plus r4. All right, so 0, 1, 4, negative 1, 0, 1, 5. I lost myself there. That was, yeah, no, that's good. Negative 2. Then 0, negative 1, that was not me, I swear. Negative 1, negative 3, and positive 1, it looks like. All right, so we know that we're supposed to get entries along the main diagonal that could be zeros or 1. Ideally 1s, but you never know. Should be lower triangular, zeros above the main diagonal. All right. What we need are the actual columns. So for the first column, we're going to take all of the entries and divide it by the pivot number within that column. So first column, first matrix. So 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3. A little bit more space. Negative 1 divided by 1 is negative 1. So then we're going to row reduce again, working off of this guy. So negative R2 plus R3, and then R2 plus R4. So we're looking at 0, 0, 1, negative 1. Then it's just simple sum, so 0, 0, 1, 0. All right, so in my second matrix, giving me my second column, we're dividing each of the column entries by the pivot number. So 1 divided by 1 is 1, 1, negative 1 divided by 1, negative 1. All right, so now we're looking at this guy. So negative R3 plus R4. Couple of 1s, it looks like. And then for the last one, it's already in echelon form, so 1 divided by 1 is 1. All right. So we have our L and we have our U. Ideally, those actually multiply to give us the matrix we started with. So just do a quick checkaroo there. Oh, damn it. Where did I hit? Go to... Oh, I didn't put a number in. That's good. Zero, one. The zero didn't take.
Where does LU decomposition even mean, if that makes sense? Like, where was this meant to represent?
Lower and upper triangular.
Alright, so I was just extending it. It's really just a strange word. Reduce it.
So the idea is to get factors of a matrix in such a way that one of the factors is a square matrix that's in lower triangular formation and the other is in upper triangular formation. Okay, so product of A and B. All right, so we have our factors. All right, now, so that carries you through this part. The idea is somehow we have to actually solve an equation from this, right? But the rest of the process isn't really anything new because it's all unit one stuff. So we went through the entire process of coming up with the L and the U. So we're good to go there. Now what we do is we find LZ equal B, right? So what that means is you have your lower value, your lower matrix, your lower triangular matrix, and some unknown variable Z, variable vector, is equal to B. B being whatever you started with. That's going to allow you to solve for some intermediate variable. And then we set our upper triangular matrix as a multiplier of x equal to that solution. And whatever that result is going to be our x. Right? So basically we're doing kind of the inverse process twice. So we're doing it with the two sets of factors rather than just once. Right? So, is it a better way to do it? I doubt it. But, because the inverse matrix approach is really just you're taking the inverse of your coefficient matrix and multiplying it by the solution vector and getting an answer. Here we're basically doing it twice. It's like, what's the purpose? Well, the purpose behind it is for you to demonstrate knowledge of the LU factorization competition. Right? So aside from that, there are other techniques that you can use. But if you look at this as the solution of an AX equals B equation, a matrix equation, what are you doing here? We're row reducing to get a solution. And then using that solution as part of another matrix equation to get, through row reduction techniques, another solution. Right? So through this process, as opposed to the other one, you can get a solution just through, well, actually, you could have got it with row reduction techniques the other way too. So, yeah, it's really just a practice LU.
If you get your L and you're doing LZ equals B, do you have to keep row reducing, or can you just put the inverse of that matrix in the calculator and then multiply it by your solution?
Oh, yeah, you could do that because it's going to be pretty easy to do it with a lower upper triangular matrix. To find an inverse, it's pretty not bad. So.
But could you just take that matrix and then multiply it by your solution?
Yeah, the inverse of the matrix. Yeah. Yeah, there's nothing wrong with that. I mean, you don't actually have to use row reduction techniques to get you there. Okay. Yeah, so once you get your L and your U, it's kind of up to you which approach you want to use.
Is there any way to
Calculator.
Okay.
Yeah, just what I did, multiply them together, see if it gets back where you started.
Okay.
Aside from that, I mean, you could do it by hand. I mean, there's a lot of zeros, so it should be pretty not bad there also. Finding the determinant. You know, let's say you wanted to use Kramer's rule to solve from here. So you got your L and your U. You set up your L Z equals B, and you want to use Kramer's rule for this. Much more convenient because your determinant is really the product down the main diagonal, which is just a 1. All right, so you're good to go there. So do your, let's say you want to do your column swapping. You know, so where do I have Kramer's rule? Down here. So I swap out, you know, going back to the original problem, I swap out column 1 with 2, 0, negative 4, 5. All right. Here it was kind of a pain. You had to go to the calculator. But if I do it here, down the diagonal, because it's lower triangular, down the diagonal, the product is just a 2 now. So I now know that the solution for Z1 is equal to 2. I can actually visually determine the solution here, because if I replace column 2 with this, I now know just by multiplying down the main diagonal what I would have as a solution. You know, so well, actually that one I'd have to do a little work because it wouldn't be lower triangular anymore. But you know, with slight adjustments, you can get your solution that way. So a lot of options, but it's really the LU factorization that matters the most.